Some of you are majoring in or thinking of majoring in neuroscience. It's funny to do a show of hands when half the class is on watching in some electronic thing at home. If you're at home, don't bother to put your hands up. Have any of you already taken a course like Neuroscience 1 or some AP, Dissect Your Own Brain in high school? Okay. And the class is written assuming that you haven't taken a class already. What we're doing is a particular strategy. It's a strategy that might differ from the next time you take a class with more detail on the brain. We're taking sort of a big to small strategy. Small to big would be to start off with the individual unit of analysis, a cell, and to spend 20 minutes talking about the functioning and the anatomy of the individual brain cell or neuron. If you've ever read the preface to the textbook, you've read an experience by a student that was identical to my own experience to the extent I remember it in college, which was to learn all that stuff and not have the foggiest idea what it had to do with any like psychological experience of a person. So what we're doing instead is to start off with some psychological experiences of a person, not just to tell stories about the individual studies, but because even though it doesn't, oh yeah, lesson, there we go, because there are some general lessons about brain functioning. Now, most of you in class won't be like, you know, doing surgery on brains for a living. Nonetheless, it's reasonable to have some working understanding in general of how the brain works because it's relevant to a lot of things, including when you ask yourself about yours or the children of the future, psychological changes, how are they affected by this, et cetera, et cetera. We're now for these 2 days, you know, briefly looking at something that clearly is one of the 2 or 3 major growth areas of the sciences in general. So there's a lot more to learn in the future, but we'll do what we can in 2 days. We're starting off with individual studies that are designed to address the question, what's the brain like? That is, how is it possible to even get started on some general principles of what the brain is like? As you'll see in the textbook, this is a question that's been asked since the time of ancient Greece and Rome, at the very least in the Western tradition, where people typically saw the brain as being like something, I don't know, that's a technology we have, like a pump, if you were in ancient Rome, where they had good pumping systems and thought that fluids and spirits were pumped around the body by the brain, like a computer. Once we had computers, it was possible to think that computers like a brain is like a computer and vice versa. One way to answer this question, though, is to not speculate. Oh, yeah, there's the cartoon. Is to not speculate, but to look at some studies that might tell you something about what the brain is like. Here's one now. This is early on in the chapter on the brain in the book, in case it seems familiar. 43 participants agreed to take part in a study that's going to last a few months. The first thing that happens in the study is that brain images are taken. Later in class, we'll say how this is done, but in some sense, it doesn't really make that much difference. It's possible to get brain images that either show something about the anatomy of the brain, like the density of brain cells in a particular area, or in some studies, to get images of what changes in the brain when a person starts doing a task compared to when they're just staring into space, not doing the task. So 43 people has these brain images, and then, oddly enough, half the people are asked to learn how to juggle. Oh yeah, another cartoon. They're asked to learn how to juggle, except not that fancy 6-ball routine. They're asked to do a standard 3-ball routine. And they're given a bunch of time to learn this. For some reason, this is not that hard if you've ever decided to juggle 3 balls, but they're given a couple of months. Just please tell us when you've learned to do this 3-ball routine and can do it for 60 seconds, which is pretty good. And then they come back, and brain images are taken again. Now, if you took images of, like, their hand, unless they were using really, really heavy balls or ones with little spikes or something, nothing much is going to change about their hand if you did a before or after on their hand. They're looking at the balls, but if you did an anatomy of the eye, not much is going to change in their eye before or after juggling. However, oh, yeah, and then again 3 months later to see if the effect is temporary or permanent. However, unlike the hand and the eye, there is a change in the brain. What happens, and the way these things work, now that we're going to see more of them, is that typically when you see an image like this, what you're looking at is a before and after image. If it's a study that involves comparisons of groups of people, it's like before and after for the people who juggled compared to before and after for the people in the control condition who didn't juggle. Some of the studies, it'll be before and after a task occurs, so people are staring into space, the task occurs, and after and during the task, there's some part of brain that's active, and typically, I mean, obviously the person's brain doesn't really turn yellow. Some kind of highlighting is done to indicate the region of the brain in which a change occurs. In this case, the change, as you can tell from this little vertical axis, is that there's a change in the actual anatomy, in the density of cell bodies in areas that researchers already know are involved in something that's relevant to juggling. Like it would have been a bad study if people were better, if some part of the brain involved in language or something had changed. What changes is some part of the brain that coordinates vision and movement. As we'll see later in class, or you'll see in the chapter, there's parts of the brain that are distinctly devoted to one stage of processing for vision, that are distinctly devoted to one aspect of moving things like your hands. For hand-eye coordination, those hand movement and eye parts of the brain obviously have to be coordinated. And if you spend a whole bunch of time juggling, when you're done, and it's pretty permanent, I mean relatively so, 3 months later, there's more brain growth, which is the technical term for brain growth. There's more brain growth in parts of the brain that involve this coordination of movement and vision. You know, it seems straightforward now, but this study, which was only done, oh, here we go, no change in jugglers, which was only done 10 or 11 or some years ago, depending upon when you get around to watching this film at home, that was done not that long ago, was totally novel at the time. So this simple study appears in one of the world's great scientific journals, Nature, and the people are telling you this is contrary to what everybody thinks. This is the first study to show a task like this. Now, a mere 11 years later, this kind of thing is common knowledge. It's referred to as brain plasticity. The idea is that unlike a rock that just can't be bent too much, plastic is movable if you heat it up, shapeable kind of thing. And the brain changes as a function of experience. Here's a second example of that. This was actually in the memory chapter of the book. It's a study of London taxi drivers. The reason London taxi drivers are interesting compared to Wilmette taxi drivers or something is that there's all these streets in London. Even if you zoom in, it seems hard to believe that anybody could just drive to the right place in London, especially because they do crazy stuff like, anybody from London? Crazy, they're insane. Crazy stuff like this. Here's Skipworth Road. Here's Ainsworth Road. Here's Frampton Park Road. It's the same road. Anyway, the question, of course, how the heck could the bus driver, who's actually driving a taxi in this case, how could the taxi driver possibly know if you're going to Ainsworth Road that it's the road that's in between the continuous Skipworth Road and Frampton Park Road, and there's this many roads here. And they're all like that. It's, anyway, what happens is they learn all this not by trial and error, by just getting lost for 3 days in a row when you get in the cab. They first have a training period. This is what it says in this paper, of 2 to 4 years acquiring the knowledge, learning the layout of 25,000 streets in the city, which change names every 100 feet. So there's the paper. It's from, again, this, not that long ago, 2009. What they do is to run actually a number of studies of taxi drivers and others. In some of the studies and for parts of the studies, people play a taxi cab simulation game. Apparently, they've got some game in which you drive in a taxi and go around and go through Trafalgar Square or something and try to avoid hitting red buses. And they also, of course, take brain images of taxi drivers and non-taxi drivers, where they're particularly interested, again, kind of like the juggling study, of, or interested in, whether there are parts of the brain that differ for taxi drivers and others, especially given that the taxi drivers have spent 2 to 4 years learning all this stuff. And they find something. What they find is differences in a particular brain region called the hippocampus, which doesn't locate in just one little space on an image, because the hippocampus, as you see, is kind of this curved substructure of the brain, so it'll show up in more than one area because it curves around. What they find is that the taxi drivers have more brain volume, not in general, not in parts of the brain that control hearing or are used for language or for vision, but in parts in a particular brain region that's known to support spatial memory, the recall of geographic layouts. If you've ever parked your car in one of those ridiculously large parking lots inside, at a shopping center or a sporting event, and then you come out hours later and have some recollection that the car is kind of over here, sort of, and then you find it. I mean, every once in a while you don't. But often you're guided by some kind of recollection, not an explicit one that you parked in X92 row, but instead some sense that, it's over here. What you're doing is obviously animals have this without having a map. They make it back to the nest or your house or something. What they got is this implicit memory, not an explicit, I, the dog, live on Main Street, but this sense of where they are based on a bunch of visual cues and a geographic layout. That uses the hippocampus. And if you spend all this time learning the 25,000 streets in London, you've got more hippocampus. However, note, I try not to reference explicitly the stuff in the book, but there is one of these. Of course, this does not actually show that the training involved in becoming a taxi driver creates more hippocampus, because, of course, I'll just spell this out instead of asking, it's too obvious. It's possible that people who already were good at remembering streets signed up for the job taxi driver, and people who tend to get lost all the time don't sign up for the job taxi driver, and the people differed before training, but they actually do have other studies in which they very recently studied the taxi drivers before the training, after the training, and there is this effect. So